All right, let's go ahead and get started. I think the balance of allowing 688 people versus the homework being due tonight, that balance is slipping one way still. So for those that are watching the video that didn't hear last time or didn't see the email, 688 students are now in any section are now welcome to come to class. I don't think we'll have any issues of number of people there, but you never know. So for now, come to class if you want, but also you don't have to. You can just keep watching the videos if you prefer. I'll get some announcements in a second. This lecture, though, is on linear regression. And really, I think actually that kind of undersells a little bit what it's about, though, because in some sense, actually, through linear regression, we're actually going to kind of talk about all of machine learning. So, and I actually mean that to some extent. So, there are certain slides here that if you fully understand and appreciate, you will actually understand machine learning better than I would say 90% of the practitioners there that actually use it in practice. That being said, these are actually quite difficult to really internalize these things, and so just having the slide and saying that is one thing, but actually kind of understanding this is another. But we're going to talk about linear regression, and we're going to talk first about a simple example of least squares regression. I'll define what I mean by least squares versus linear regression throughout the lecture. These two terms are often used together, but I'm going to mean very specific things by each different term. So it's important that I'm using those two terms differently, least squares versus linear regression. I'll then introduce some machine learning notation. And this is probably the part where we really do cover almost all machine learning, because what we're going to do is we're going to frame linear regression as a machine learning algorithm in the context of virtually all other machine learning algorithms. So we're going to talk about what it is to be a machine learning algorithm and sort of what components you need to define a machine learning algorithm. And then in the rest of this course, we're going to return to that a lot. We're going to come back to these ideas of these needing to define these things and needing to kind of build on these themes. After that, I'm going to revisit linear regression now in this sort of broader context and define it a little bit more formally with a little bit more mathematical notation. So we'll cover that. I suspect we'll get partway through that by the end of lecture today. That's fine. Actually, if we cover everything in this lecture, the next lecture, which is linear classification, is going to be very short, because actually it's almost everything that we cover here almost remains unchanged, with one very small difference when we move to classification. So really, this lecture is really the next two lectures in some sense. And then finally, we'll talk about implementation, which is going to be pretty brief here, because unlike some of the later topics, I don't want people going to scikit-learn to implement linear regression. It's easy enough that you should just know the equations, know how to solve it. If you need to do things like cross-validation, yes, you can certainly use scikit-learn. But for a lot of simple things, it's really good to learn how to use just kind of raw math to implement these things. So I'll just highlight the code that does that. I should also mention there's also all the data and code from this lecture are also up on the web page, so you can take a look at that notebook as well. It's just the code. It's not documented really or have text or anything, but it's the code itself and the data that does this is all there. Okay, so as probably everyone knows here, homework 2 has been pushed back until tonight at midnight, but, and this is, we'll see how this actually plays out in the end. There are no late days allowed after tonight. The idea was this was actually giving everyone late days, but unfortunately it's kind of hard to actually internalize that. So the upshot is that it's just due tonight. And be sure to submit early, submit often. You can get partial credit as much as we're sort of able to give with the auto grader. So submit, make sure your code's running well before midnight tonight. Homework 3 is also out. So homework 3 is on the website now. It's due next Wednesday as usual. We're going to try to get back to the schedule. Depending on how the auto graders shake out, we may have to push it back again, but I hope not. You should have all by now received feedback on your tutorial sentence description. For the most part, it was just one word good. But I wrote a little note about this to the class. By far, the biggest problem with a lot of the proposals was that they cover something which we're going to cover in the intervening time between now and when the tutorial is due. And that's not really fair, right? So both for the people doing it and for the other people, because they're doing a topic that's covered, and what else do you describe in your tutorial? So I realize that's actually hard to know because we haven't released all the topics, but I covered kind of a list of the algorithms we're going to cover. And if it covers one of those, then you should probably pick a different algorithm. If you have any questions about that, though, I'm going to hold extra office hours just for that today, not for the homework. If I have downtime there, I'll be answering questions on the homework, but it's the office hours really are for the tutorial. We'll have more on this on Wednesday if you'd rather go to the office hours for the homeworks. Finally, those people that were switching from 688 to 388, the other way should be all set. So everyone in 388 that wants to switch to 688 should be enrolled. The other way we ran into a little bit difficulties, I think, just because you're downgrading units, they needed a form signed. So email me, I'll send you the form you need to sign, and then you have to have not your department head, but your academic advisor sign it too. I've done this before. I didn't require that before, but I guess this time they're asking for it. And finally, I have a little. I have to admit this, I misspelled Dijkstra's algorithm constantly in the slides and in the handout. I think it got wrong in my spell corrector somehow, and then I just started typing it that way. It was not just a typo, it was actually spelling it incorrectly. But I can't even blame that fully, because I think I even spelled it incorrectly once again after that. So I even messed up again. But I fixed the slides. The handout's still the way it is, because I don't want to change that. Upload a new version the day of that's due, but we'll fix that long term. But unfortunately, the video is there for all posterity, that explaining that I actually don't know how to spell Dijkstra, one of the most famous computer scientists in the history of computer science. So apologies to him, and apologies to everyone that probably will also carry on this misspelling now forever, because you've also internalized it. But it's Dijkstra. It's a hard name to spell, but I really should have known that. He's a very famous computer scientist. So, and I did know it, in fact, but I repeatedly messed it up. So slides are fixed now, but videos are not fixed. So this will serve as my apology on tape. OK, any questions about this? All right, so let's jump into least squares. And what I'm going to do is I'm going to first, as sort of indicated by the outline, I'm going to first start with an example of a task we can solve with linear regression. And then I'll move towards, first then towards solving it in this kind of small, restricted sense. And then I'll form a more broad kind of definition and solve those in a more general way. But out of curiosity, who here has seen linear regression before? Who has used it before? Okay, so most people, which is actually a good thing. So I'm curious, actually, how this presentation will jive with what you've seen before. It probably will pretty well. I mean, they're all equivalent, but there are a lot of ways you can present it. And I'm taking kind of the machine learning way of presenting least squares, least squares and linear regression. All right. Let's take a simple example to start off with. And actually, this is all real data. This data, I work a lot in applications and power systems. This is data that I had handy, but it's included in the course webpage if you're curious. And the question I want to answer through some analysis here is, how much power is the Pittsburgh area going to consume tomorrow? Well, electrical power. And there's a lot of things that affect our consumption of electrical power. And it's actually a really important problem, because if we know ahead of time, and say, let's also actually answer the question, what's the maximum power consumption going to be tomorrow? So at its peak, how much electricity are we going to be requiring in Pittsburgh? This is actually a very important problem from a lot of standpoints, because if we know in advance how much power we're going to consume, we can pre-schedule more efficient generation to provide that power, rather than having to kind of start up power plants at the last minute, which oftentimes are dirtier and release more emissions and cause all sorts of problems. I'll also lead to things like instability if you have to do this too often. So it's actually a very important question. How much power is the area going to consume tomorrow? And I want to talk about how we might come up with an answer about that. Now, if you talk about a question like that, it's very hard to kind of just a priori think about this and make some estimate, right? Maybe you think, okay, well, what's the population of Pittsburgh? Can I go back to first principles of how much electricity we think people are going to consume? People have TVs, people have laptops, et cetera. It really, you could go down that route, but you'd probably not get very far. You'd probably have, maybe the right order of magnitude in your estimate, but it's not going to actually give you a good answer you can schedule things on. So it's actually very hard to come up with a priori model. It's sort of a first principles model to describe something like that. On the other hand, though, it's relatively easy to come up with a data set that includes for all past days what the peak demand actually was, as well as what were some other characteristics that may affect that peak load. The obvious one being temperature, right? So when temperature is high, especially in the summer, people use a lot more air conditioning, and that causes the whole region to use a lot more electrical power. So what I can do then is I can come up with a table that lists all, for all the dates that we have, that we care about. In fact, at first we're here going to only talk about summer months. So we're going to talk about June, July, and August for the months, because that's when air conditioning is the most prevalent and causes the biggest increase in demand. For all these dates, going back, I think I go back 6 years here, I'm going to look at the high temperature that day, and I'm going to look at the peak electrical demand for that day. This is all public data. You can download it from weather sites and from the system operator that coordinates the generation of electricity in the region, which is an operator called PJM. You can download it from their site, and I even just have links to it, or I just have the data files themselves in the code you can download. So I can take a bunch of these things, and then for each day you have a high temperature and a peak demand. And if you take 6 years or so and plot this on a chart, again, just for the summer months, it looks something like this. So this is now every day. What was the high temperature that day? It's not perfect because they're kind of discretized, so you can kind of see. Interestingly, it's not discretized on even increments, but they're clearly kind of discrete bins here. But we'll ignore that, and we'll just pretend it's continuous data. So you have the high temperature on the x-axis here, and the peak demand on the y-axis. And what we see is kind of as expected, right? There is this nice kind of increasing trend where when the temperature is higher, we tend to use more electricity. And that is because, in the summer at least, the demand for electricity is largely driven by air conditioning. And that increases. It's actually not linear. It's actually a different kind of function, but empirically it actually looks fairly linear. It's like you could draw a straight line through this, which is in fact exactly what we're going to do in a second. So this kind of leads immediately to the idea of, well, let's try to fit a model that can describe this data, right? So let's try to fit a model that will predict for a given day, for a given high temperature, what is the peak demand going to be? Right? And the way we can do that, a simple way we can do that, is fit a linear model, right? So we're going to fit a model where we approximate the peak demand on any given day as some coefficient times the high temperature plus some other coefficient, where the theta 1 here is the slope of that line, and theta 2 is the intercept of that line, right? Now, the question is, how do we fit this line to data? Okay, so how do I get the best line that, in some sense, fits that data as well as possible? Obviously, you can't have a line that goes exactly through these points, right? There, in fact, is a single, there are multiple x's here that are the same, that have different y values. So you're not going to actually get a perfect fit, clearly, to this data. But you can still imagine that a line that goes like this would be somehow better than a line that goes like this, right? That wouldn't really capture the actual intuition of the data. How do we fit a line that can actually capture the behavior here? And so what we're going to do is we're going to talk, and there are actually a lot of ways you can do this, and we'll talk about a few later on in class. But the idea of what's called least squares regression, or least squares modeling, says that we want to find the line that minimizes the sum of squared errors between our model's prediction and the actual observations. Right? So that's really the key point here. And I'll return to this a lot, because this is actually kind of the key element, not just of this algorithm, but really of almost all machine learning, which we'll get to much more generally in a second. So we sum over all I, which is over all days, multiply our high temperature of that day. I'm using the notation here, a little superscript for the high temperature of that day, times our first coefficient plus a second one. This term here is our prediction for that day. And we subtract off the actual peak demand that day, and we square the difference. Right? Now we want to find coefficients, theta 1 and theta 2, that make this expression as small as possible. Maybe I'll write over here, because I'm going to start writing the board quick soon, and it might be hard for some people to see. Can everyone see that one over there? OK, I'll use this one. OK, so now how do we find the theta 1 and theta 2 that actually minimize that? I'm going to, in fact, put this up. Now, left. Never know if this is the left or this is the right. This is the left, according to the system. All right, so what we want to do is we want to find parameters that people get there. If you can't quite see from over there, feel free to move over to that side. OK. We want to find parameters that, that minimize this sum of squared errors, right? So how do we find these parameters? So I'm going to write this as the following way. I'm going to write it as a sum over all I. I'm going to omit the days, you know, I'm summing over all days here, of theta 1 times xi, where x here is going to represent the high temperature, plus theta 2 minus yi, where y is going to represent our peak demand. Now, the basic idea that we're going to use here is one from calculus. And hopefully everyone's taken some calculus. It's really simple calculus we actually use here. It's just derivatives. There's no integrals involved here. Just derivatives. In fact, it's like two derivatives you have to know. It's just when you square something, I take the derivative there. And what's the chain rule? But I'll write it all down. Hopefully that will, everyone will be familiar with that. If not, I can give some references to pointers on calculus references. But the idea is, if we want to minimize some function, and there definitely are conditions on this function, like it has to have a minimum, not a maximum, right? If we want to minimize the function, then we need to, be such that the function has a minimum and not just looks like this basically and not like this. I'm not going to be formal about that right now, just because I don't want to get too formal about what this means. But if the function looks like this, but has, say, only one local minima, then we know that the point where there's zero derivative, the derivative of that function is 0, that's going to be a minimum of that function. Right? The derivative, remember, is just the slope of a function. And so the point where it's 0 is going to be a minimum of that function. If you do have multiple ones, actually, there can be a point here which also has 0 and a point here that also is 0. But we're not going to worry about the functions just yet, even though we will encounter them later in the class. For now, we'll assume every function kind of looks nice like this. OK, so we want to find a point where the derivative is 0, right? And in fact, if we have a function like this, which is really a function of two things, we want both their derivatives to be equal to 0. Now, I'm going to write this sort of out term by term to start with, but quite soon we'll get to a more complex definition, which that might be new for some people, but hopefully it isn't too complicated either. OK, so let's now take derivatives of this thing and try to find a point where the derivatives of this function, thinking of this as a function of these two parameters, because we're trying to minimize over those two parameters, we're going to try to find a point where those two derivatives are equal to 0. All right, so let's first, well, we can write them both out, what the derivatives are. So we can take a derivative, and this notation here is called a partial derivative. All it signifies is that this function, thinking of this quantity here as a function, depends on more than just theta 1 and theta 2. And when that's the case, you write these kind of scripty looking d's rather than normal looking d's, or rather than like ticks for the function. It's just math notation. OK, so the partial derivative of this thing, though, I'm just going to differentiate this whole thing with respect to, in this case, I'll do theta 1 first. Right? So hopefully everyone remembers this, but if you have a derivative of a sum, you can exchange that order. So you can take the sum of derivatives here. When I take a derivative of some term squared, I apply the chain rule and take this whole term just without the square, actually with a 2 in front of it, times the derivative of what's inside here. So this is going to be equal to the sum over all I of this guy, well, 2 times this guy, theta 1 xi plus theta 2 minus yi times the derivative of what's inside here. And the derivative of this thing with respect to theta 1 is just xi, because that's the only term that depends on, that multiplies theta 1, so times xi. I think I write that in a little different order there. I put the xi first, some of the 2 out, but it's of course all the same. Okay. So that's the derivative with respect to theta 1. The derivative with respect to theta 2, actually even easier. It's pretty much the same thing, but in fact, because theta 2 doesn't have any coefficients on it here, it's just, there's no x on the outside. So it's just equal to of this guy. The derivative of that guy. It's getting kind of, it's just equal to the sum over all I of 2 theta 1 xi plus theta 2 minus yi. Okay? Those are our derivatives. And now I'm going to set them both equal to 0. And the way I'm going to do this is I'm going to first set this one equal to 0, and then plug in the solution into that one, and then solve for theta. So solve for theta 2. This is going to involve theta 1 still. Then plug in the solution to theta 2 here, solve for theta 1, and that gives me my solutions. So I'm going to take this whole quantity here and set it equal to 0. Just that everything's still scalar value here. These are just all scalar numbers. We'll get to vectors shortly. Get to that kind of fun soon. Okay, so what does that mean? Well, that just means basically we take this term out, right? So we have 2 times the sum over all I of theta 2. There's actually no dependence on I in that sum. But that would be equal to the sum over all I, and I make sure actually, yeah, of it's going to be negative here, theta 1 xi minus yi. Or in other words, theta 2 is just equal to the because basically when I sum this over here, I just get m, or m is the number of examples I have, times theta 2. So this is 1 over, in this case, the number of days times the sum over all I of yi minus theta 1 xi, which is just equal to, I'm writing it like this, y bar minus theta 1 x bar, or these are the average values of y and x1 or xi over the data set. Does everyone follow what I was doing there? So it's just algebra. I mean, I'm just manipulating this, moving things inside sums. I guess the one thing here is just to make sure this clear. This term here is equal to 2 times the number of days times theta 2. Right, because it doesn't depend on I, so I just sum this. I just multiply by the number of terms that I'm summing over, which is just the number of days. Sorry, I used the word, I realized while I was speaking, I used the term m, which I'm going to introduce later, but I haven't actually introduced that yet, so ignore what I said about m, or the size of these things. Just the number of days. So that is our solution. This is our solution here to theta 2. And that thing is going to be stuck forever. I don't think we're ever going to get that out. It's going to be hard to push this thing forever. Okay, questions so far? I know there probably are some. Feel free to ask it. All right. Well, assuming there are no questions, really. What we're going to do now is we're going to take that solution there and plug it in to our expression for theta 1. So we want this guy, which is the sum over all I of 2. And I also dropped the 2, notice, because the 2 is on both sides. Oh, I forgot a 2 here. The 2 is on both sides, so I can just divide through it. I often leave it out. Actually, later what people do is they add a 1/2 to the thing you're minimizing just to get rid of it. But it's sort of incidental. Okay, anyway, I'm going to take the expression for the derivative with respect to theta 1, which is going to be 2 theta 1 xi plus theta 2, which is in this case minus theta 1 x bar plus y bar minus yi. I want times xi, right? That's my derivative up there. I want this to be equal to 0. So now I do the same thing, right? I group all the terms that depend on theta 1 together. So what I'm going to get is I'm going to get theta 1 times 2 sum over all I xi and xi minus x bar. So this is the terms that depend on theta 1, right? You have this term here, they all multiply by x1. This is going to be equal to the sum, all the terms that don't depend on theta 1, which is sum over all I, 2 xi, which direction is it? Yi minus y bar. And so the actual solution is just theta 1 equals this term over this term, which is what we have there. Once you find theta 1, then you just plug it back into your solution for theta 2, and you have theta 2. And in fact, if I do that for this system, this data that I have, I get the solution theta 1 equals 0.46. That's the slope of the line. And then the offset of the line is negative 1.489. Questions? I'm going to wait a while for this because, actually, as a question to you then, when people learned linear regression before, did you learn it this way? Is this how you were taught it, or did you learn it in terms of like projections, or minimizing norm projections? Yeah.
First, I learned it twice, like two machines. One in undergrad, one here in 601. But the one in undergrad, we learned it a little bit more visually.
Yeah.
We didn't delve into too much of the mathematics, the derivations. We see like animations where we see squares and we were trying to
Yeah.
find those small squares. But then 601, we did more derivation, but we didn't that much.
Okay. So people have seen something like this before? All right. I want to make sure because it's going to get a lot trickier in a second. So I want to make sure that this at least makes sense. To be honest, to me, I'll be frank too. To me, so we're going to switch to a second from using this kind of term-by-term math to using vector and matrix math. The vector matrix notation to me is actually much simpler. This stuff like just gets me, all the sums and everything gets me confused. When it's a nice vector and matrix, it's really easy for me. So we'll see that in a second. But it's important to know that everything does just come back to these sort of simple rules of single variate calculus that you can always fall back on if something is kind of tricky here. So if I run this now, so if I figure out what what theta 1 and theta 2 are based upon these equations, and I plot the line over my data, it looks like this. So what I'm doing here is essentially I'm looking at every point. Effectively, I'm not doing every point because there's a line, so I'm just taking 2 points. But if I look at every point, and for this point here, multiply 80 degrees by that, by whatever theta 1 is there, this value here, and then subtract 1.489, I get that value of the line. And I get the same for all the values of the line. That's how I plot and sweep out that line. And what's sort of important here is that you could also think of this as making predictions, not just in terms of fitting data, but actually in terms of a predictive model. It's kind of really the key element in some ways, is that what we can actually use this model for is not just to tell us, from what we saw so far, we know that, in the past, this line is as close as it can be to the data points. What we really care about is that we can use this model to give us predictions. So if I know tomorrow is going to be 72 degrees outside, I can use this model. I guess it doesn't really apply here because we're outside the months we trained it on, but ignoring that for a moment. I can use this model to predict how much demand is going to be. So I take 72. Again, I'm also going to ignore the fact that 72 degrees is like a weather forecast, which is also a prediction. So let's just ignore all that. Let's assume that we know it's going to be 72 degrees tomorrow. We'll put 72 degrees by theta 1, add theta 2, and I get my prediction now of 1.821 gigawatts. And that is exactly just where that line lies at the 72 degree point here. So that's just this point right here on that line. But it's important to know that this is not just sort of descriptive. This is actually predictive too, because we are making predictions from this data about what we think given some new temperature. Okay, so now we're going to start jumping into the more complicated stuff here. And we're going to ask a few questions. Let's see. I can slide this one up? Yeah. Doesn't really matter, I guess. We're going to quickly, we can forget it because you're going to have new math very soon. So what if we want, so I'm just going to throw out some extensions, right? What if I want to also use, in addition to just the temperature, the day of the week? Or maybe even just, is it a weekend or a weekday? If I want to use that information to say how much power we're going to consume. This is actually a good one too. People use a lot different consumption based upon, clearly there was a strong correlation between consumption and temperature. There also is a definite effect of consumption and the day of the week, which we'll actually see in a second. So on weekdays, typically consumption is higher than on weekends. A lot more offices are running and stuff like that, so consumption is higher. How would we do that? Well, it would actually be kind of a pain to do it this way, right? You have to derive that many more equations. For each one, you have a new equation for it. You solve that. That would get to be a kind of a pain. I don't want to have to write down an algorithm that requires a different formula depending on how many features I have, because that would require essentially an infinite number of formulas to write down. What if I want to use a different loss function? So I kind of said, okay, we're going to use the squared error between the prediction and the actual value to measure how wrong we were in some sense. And why did I choose squared error? Why not like absolute error, right? That seems to kind of make more sense sometimes, right? In fact, I would argue the only reason people actually use squared error is because it leads to a nice solution, not because it actually means something fundamentally. Though you can kind of justify it in other ways as well. What if I wanted to use a nonlinear predictor instead of a linear one, right? So what if I wanted to use some arbitrary function rather than just lines to fit the data? Like polynomials, but also fancier than that too, even fully nonlinear functions where you can't even write it down as any kind of linear function. All these things kind of make this a little bit tricky and make us want to have a more general notation for how we write these things. So what I'm going to do is I'm going to switch now from linear regression to kind of generally machine learning. And this is going to be, as I said, the ideas here are actually cover almost all machine learning algorithms you will encounter. They are not often taught this way. We will teach them this way. But it turns out that virtually every machine learning algorithm can be understood in this same context. And I think it's really valuable to sort of see that because it really brings together a lot of different algorithms into one fold. So what we've done so far has been an example of a machine learning algorithm. Now, I don't want to sort of, a lot of people sort of say, well, least squares has been around since Gauss, right? 200 years that it predates machine learning. That's certainly true. These algorithms, a lot of them actually, by far predate the term machine learning. Machine learning sort of arose as a computational way of dealing with similar questions. But given the current presentation, it's actually much better if you understand all these algorithms within one context, because they're really all doing the same thing. They're just doing it in slightly different ways. And so we're going to call linear regression, and actually this was least squares regression in particular, a machine learning algorithm. All right, so just be clear on that I'm calling these all machine learning algorithms. And so the core, so what makes something a machine learning algorithm? Well, the core idea of machine learning is that there are a lot of systems where it's very difficult to a priori build, say, a predictive model of that system, right? It's very hard to just think about, use your own, just your brain to think and say, okay, I think that consumption will correlate with temperature in this way. There's no way you could have ever done that without looking at the data first, right? In fact, this class is all about data science, so in fact, we really want to always use the data to tell us things. And this is exactly what machine learning does. It says, instead of trying to a priori build a model, right, to write a program that makes some predictions, we're going to just collect a lot of data that kind of demonstrate or that give us the mapping that we want, right? The input of the system as well as the actual output we want. And then we're going to have the actual algorithm or the computer learn how to model that data, how to model that predictive process. And that really is all that machine learning is. That's the core idea. And I should be clear. That actually is all of what's called supervised learning is. There are other forms of machine learning that we will talk about, but actually they really fit almost into the same paradigm as well. Okay, so now I'm going to, and so the idea here, so the basic process of machine learning is that we have some training data that is sets of inputs and outputs that we want to be able to predict. So given this x1, our algorithm should return something close to y1. Given x2, our algorithm should return something close to y2. And we generate what's called a hypothesis function. So we have we learn some function that for the given inputs we've seen so far, returns something close to the outputs, where that sort of closeness is going to be a lot more rigorously defined in a second. And then in the final stage of machine learning, we get some new example that we haven't seen before, some new example x. And this is an example where probably we don't actually know what the actual what the actual true output is. If I say tomorrow, we know it's going to be 72 degrees, but I don't know what the peak demand is going to be. The prediction phase of machine learning says, run that example through my hypothesis function to generate a prediction of what I think the output is. Right? And that really is machine learning, or it's supervised learning, to be clear, to be precise. So let's talk about the ingredients of machine learning now. And as I said, this is actually going to be, these next 3 slides will cover all of machine learning, almost. So learn them well. You can go back to them a few times if you want. Okay, so, and it's really actually just terminology, because that's all machine learning is. And we've been also very bad at it, by the way. We're great at marketing terms. We're great at coming up with like cool names like support vector machines and neural networks, but we've been bad at kind of clarifying exactly how they all relate to each other. So let me try to describe that. Okay, so there are, I would say, 5 ingredients. Well, 5 things I'm going to define here, and really 3 ingredients to a machine learning algorithm. The first thing I'm going to talk about is the input. And the input, we're going to talk about input features. Features. And these are the inputs to the algorithm, right? The inputs to our machine learning process. They are what we give the algorithm in order to make our prediction. To be clear, they're what we give the hypothesis function to make our prediction, right? And so we're talking about features. We'll call them xi to denote the ith feature. And we're going to think of these as vectors that live in some space Rn. So they are n-dimensional vectors. They can be they could be discrete, they could be other forms, but I'm going to think of them as being real-valued vectors. We'll talk in a little bit later how we encode things like discrete values with real-valued vectors. Those are input features. The second thing we have is our outputs. And an example of this, is what we had before. Say it's the high temperature at day I. Maybe we add things like, is it day I a weekday? And then actually also for convenience, I'm going to wrap that constant term into the features themselves. So remember, when we went back, we actually had this additional term here, theta 2. They didn't multiply any of our inputs, just multiplied 1. So to make it a little bit simpler, the notation, I'm actually going to wrap a constant feature in there so I can actually talk about our predictions as being just a linear function of some parameters and our input. But we're also going to think of one of our features as being actually the constant value 1. We also have outputs, y. These are going to be in some space y. And I'll call them yi. I should also say here that in all cases here, I is going to vary from 1 to m. So importantly, m here is going to always be the number of examples we have in our data set. Whereas n is the number of the size, the dimensionality of each input to the algorithm. Okay, so yi could be actually in a lot of spaces. Here, for example, when we talk about classification, we'll talk about these things being discrete valued. But for now, when we're talking about regression, that just means that the yi's here are real valued too. So our peak demand, for instance, which will be an example here, is a real valued quantity. All right, we have parameters. And parameters are denoted theta. And here, I'm actually going to make an additional assumption. This is not always the case, but here I'm going to assume, or specify, that our number of parameters are actually going to always be equal to our number, to the dimensionality of our input vectors. Not always the case, and we'll soon get cases where this is not the case, but for now I'll leave it like that. Okay, so next we have hypothesis functions, which is just essentially a mapping from inputs to outputs. So I'm going to write this as h sub theta, which maps from Rn to y. So this is a function that takes inputs as its input features as its inputs, and outputs some value in our output space. And we have many forms here, but one example form we can talk about so far is the linear hypothesis. Which just says that h theta of x is equal to theta transpose x. Remember, theta here and x are both vectors, so this is an inner product of the two vectors that's equal to the sum over all I from 1 to n of theta I x I. I think I used j there just because I'm using I here, so let me just use j. So from j equals 1 to n of x theta j xj. I usually avoid indexing in to the thetas or the x's here. That's kind of what actually linear algebra buys us, so we don't have to worry about that, but we can always if we want to. Importantly, but actually on that point, I'm going to use superscripts always to index over multiple different examples. So x superscript in parentheses 1 would be the first day, for example. X superscript 2 would be the second day. Whereas I'm going to use subscripts to index into elements in a vector. So x superscript 1, something like this. So, x 1, 2 would be equal to the is weekday flag on the first example. Okay, so we're almost there to all of machine learning. That's the first slide. Okay, everyone still with me? All right. Second slide. The final sort of the 5 ingredients, I guess, and then I'll talk about the 3 things we need, is what's called a loss function. And this is going to be function. And this is going to be how we measure. This is a function which I'm going to call L, which is takes 2 outputs and then outputs a real, in fact, positive number. And this is a way of measuring how close the prediction of a hypothesis function is to the actual value. So one of these 2 y's here is a prediction. I'll, by convention, use the first one being a prediction. The next one is the actual. And depending on how different these 2 are, we're going to get some positive real number there. Now, I'll actually change this a little bit when I talk about next time about classification, but we'll get to that when we talk about it. There's one small change I'm going to make, but for now you can think about it like this. So for example, the squared loss would be a sort of a natural way of measuring difference, right? We do require loss functions to be positive. If they are negative and bounded below, you can always just add a constant to make them positive. If they go off to infinity forever, it doesn't really make sense because that means we can keep getting sort of less and less loss, which doesn't really make sense. So these have to be always assumed to be positive. You can't have them be negative. So squared error would be 1, right? That's a positive quantity that is bigger the farther apart these 2 things are, and it's smaller when they're closer together, right? So a loss function should, in general, be big when the predicted value is very far from the true value, and small if they are, in fact, 0, typically, if they are the same. So that's our loss. And so now, I am finally ready to write every machine learning algorithm that there is. Sort of. There are a few changes, but this is pretty much it. All right. Our machine learning, the canonical machine learning problem is we want to minimize over theta. So that means we want to find the theta that minimizes this following quantity. This is called an optimization problem. And we will talk a lot about them through class, but we're going to introduce them sort of as they come up, not necessarily as their own topic, though optimization is really its topic in and of itself. So we want to minimize over theta the sum from I equals 1 to m, so the sum over all our examples of the loss between our hypothesis on that example and the actual output. So it kind of makes sense, right? We have some type of hypothesis that's going to try to make predictions on our data. We want to minimize, basically get those predictions to be as close as possible to the true values, where closeness is measured by this loss function. So we want to minimize the sum of losses over our examples, all m of them, of this loss function. And to define a machine learning algorithm, you just really need three ingredients. You need to say, what is this hypothesis function? What is this loss function? So this is part one. Part two is what is this loss function? And part three is how do you minimize? And if you specify all those things, you can describe any machine learning algorithm. So the rest is just kind of details, right? Said in a sort of somewhat tongue-in-cheek, but not that tongue-in-cheek. Because all of machine learning, really every algorithm you come across, is just going to be a way of defining these three things. Now, of course, there are a lot of other issues that come up too. There are things like generalization error. So how well does it do not just on the data you train it on, but how well does it do it on a new data set, right? So we're going to talk about that a lot more. And I hesitate to say that this is certainly not all there is. But from an algorithmic standpoint, this is how algorithms really work. Even ones that you wouldn't think are really defined like that, typically can be cast, and I think should be cast in this way, because it makes a lot clearer how these things are all related to each other. So I'm going to give a few examples now. And this is, I think, hopefully where some of this will start to, if you've heard of some of these things before, probably have not heard of them in this way. And so hopefully some of these things will kind of, not maybe right now, but start later to make sense. OK, so the thing I'll sort of add here is that we meaning sort of me and the machine learning community, we've been very bad at being precise in our terminology here. So when we say a machine learning algorithm, we really should be talking about all three of these things. What hypothesis function do you use? What sort of model class do you use? What loss function do you use? And how do you optimize it? But it's more common, actually, just as people talk, to have algorithms, this notion of machine learning algorithm, actually only refer to some of these things. And others are left kind of up to whatever people want to do. They're oftentimes kind of implied, but they are oftentimes left free to the practitioner, which causes a lot of confusion when people describe what algorithm they use for a machine learning task, because sometimes they're actually not being precise enough. So I'm going to try very, very hard, and I might make this mistake sometimes too, but I'm going to try very hard throughout this course to always be very specific when I talk about a machine learning algorithm, to always define all its aspects. Right? What representation are we using? How are we measuring the error? What loss function are we using? And how do we optimize it? Right? But let me give a few examples about what people mean when they say some machine learning algorithm. So least squares, right? Least squares as a algorithm typically means what we saw before, which is a linear hypothesis class, first of all. Squared error, that's where this least squares comes in. So when you say least squares, you always mean squared error. And then third, it usually means an analytical solution using essentially an extension of the method we used before, which is solve for by finding derivatives. We'll in a sec talk about the generalization of that to as many inputs as you want, but it almost all, when people say least squares, they almost always mean the solution given by this exact procedure. You can solve it other ways, by the way, too, but that's what they usually mean when they say least squares. On the flip side, linear regression actually is a more broad term. That term usually just means a linear hypothesis class, where you can use other loss functions potentially, and where you can use other ways of optimizing it. So, for example, what we're going to talk about in a second later on is using an absolute loss. That would still, in some people's sort of books, and this actually unfortunately varies a lot, that would still, at least in my mind, be linear regression, because we're still using a linear function to approximate data. We're just using a different loss function and a different way of optimizing it. They have other names too, by the way, things like robust regression or least absolute deviations for an absolute loss. But I would call all of those under the class of linear regression. Now it gets sort of really fun here. So a support vector machine, right? Sounds like a very complex thing. Right? And support vector machines What those mean is that means a linear, or actually what's called a kernel hypothesis class. We'll get to kernels a little bit later when we talk about SVMs, but they're actually themselves just linear. They're just a different definition for what the features are as what they actually are. They're still linear. So some linear or kind of fancy linear hypothesis class, and a very particular loss called a hinge loss. And you can optimize it however you want. There are different ways, algorithms like SMO, or just gradient descent actually is now the most common. And that's a support vector machine. And if you see it, I mean, oftentimes when you'll talk about support vector machines, you'll see it written in terms like a geometric intuition about margins and separating half planes and stuff like this. That's all true, but I personally like this definition better because it captures just how similar they are. And we'll talk about that when we talk about classification. We'll talk about support vector machines, and we talk about it later actually also when we talk about kernels a little bit. A neural network, and realize here that also, that the stars come in different places here. So different algorithms refer to either, a hypothesis class or a hypothesis class and some algorithm or some other combination, or some loss function in the case of support vector machines. But really, we've been very imprecise here. So it's okay to use that terminology. Just when you use it, be very sort of clear that you are using it to describe these components of the algorithm. And you then have to say, if I talk about a support vector machine, I have to say, if I'm using a kernel or a linear hypothesis class, and I have to say what algorithm I'm using to actually optimize it, or I'm not fully describing the algorithm, right? And if you just run scikit-learn, it's picking some in the background there, and you should know what it's picking to know what algorithm you're actually running on the data. A neural network. So we really have great names in machine learning too. We really succeeded in that if we have not succeeded in precision here. A neural network refers to a specific type of a hypothesis function, which involves composed nonlinear functions of a specific type. That's a neural network. And it can use whatever loss you want, actually. People use the same terminology, neural network, when they use a squared loss or when they use a classification loss. They still call it a neural network. And they usually use gradient descent to optimize it, though even that is sometimes different, but that's almost always the case. So that's a neural network. And oftentimes, gradient descent in neural networks takes the name, goes by the name of backpropagation. So that is almost always how you train them. A question there, yeah. What was that? So it means multiple nonlinear functions that are composed together. So one applied to in a chain, one after the other. One to the result of the last one. Yeah. We'll talk about that a lot more when we talk about deep learning and neural networks. Decision trees. These are they're sort of trees of decisions you can go down. So you basically look at one feature, say is this one bigger or less than a certain value? If it's less than, you go down some other path. But what this actually represents, kind of from a hypothesis standpoint, is the final function are these actually the sort of nested half planes, where you say everything on this side of the space goes down one path, everything over here goes down another path. Again, all these things, don't worry about this. We're going to talk about this all a lot more. I'm just kind of trying to preview what we're going to see going forward. And they're almost always, we can use actually a bunch of different losses potentially. Those lead to different splitting rules for how you choose how to split the tree. And we typically, though, always use greedy optimization because you can't do anything else really for decision trees. That's sort of really the only option you have. And finally, naive Bayes. It is also actually a linear hypothesis class. Its loss function is actually the negative joint probability under certain independence assumptions, and you optimize it actually just by counting certain counts. And so these things are often presented in really different ways in most machine learning classes even, and we're not going to do that here because fundamentally, and I think this is actually an important component of data science, is that when you have this whole toolkit at your disposal, you have all these algorithms that you could run, you need to understand how they're all actually fairly similar to each other. And why they're all, why might you want to run one instead of the other? Well, that really has to do just, with maybe your particular data, or maybe you're just more familiar with one algorithm than the other one. So yes, that's why you want to run one over the other. But their similarities, I think, are much more important than their differences. Okay, so that was all I'm going to say about machine learning for now. What I'm going to do next is go back to linear regression and talk about how we can solve it in a more general way, using this notation here of hypothesis functions and optimization and these kind of terms. Any questions before I go on? Hopefully that gets everyone primed for seeing the rest of machine learning. But maybe it's actually not going to be excited then, because now that you realize they're all just the same thing. Okay, so we're not going to get all the way through this time, I don't think. Maybe we will, but we probably won't. Which is fine, because once I get through it, as I said, the next lecture is really actually quite short. So I wish I had another board here, but I don't, because I can't push this one up any further. It really is not going to come out. It really is not going to come out, that thing. Wonder how someone got it in there. Okay, well, I'll just try to... There we go. I got it too far, even. Okay. I want to keep all those things up because I want to keep referring to them. I will erase the numbers, though. No, maybe I'll leave the numbers up. Okay, so let's talk about least squares now. And we can now define least squares actually pretty formally by just specifying those three things. Right? So first of all, one, linear hypothesis function. That's our hypothesis class for least squares. We take the inner product of the input features and the parameters and predict that. Ingredient 2, the loss function, the squared error. In fact, I'll actually even add a 1/2 here to get rid of that. I think I erased it, but get rid of that annoying 2 that showed up everywhere. I'm just going to put a 1/2 there. It doesn't matter, it just scales it, right? And number 3, how do I optimize it? I'm going to do it by setting derivatives to 0. So that is least squares. And I'll try to use that. I often will slip into this too, where I use linear regression and least squares interchangeably. It's very common to do that because by far the most common type of linear regression is least squares regression. But I'll try to be specific about always saying least squares when I mean that, as opposed to linear regression, which usually just means the first one of these things and could mean anything else for the next two. Okay, so our problem then that we want to solve is we want to solve this problem here, right? Minimize over theta, this thing, which in the case of least squares involves minimize over theta, the sum from I equals 1 to m of theta transpose xi minus yi squared. Okay, now's where we get to be. I don't have all my board space here. Maybe I'll try that again. Push it up even further. I kind of would rather have this one. Okay, did my best there. Okay, now is where I'm going to get a little bit fancy with the math, though really not that fancy, because these sums and these sort of individual scalar things that are squared, I don't really like those. They just clutter up notation, frankly, and they make it harder to derive the solution when you use matrix algebra. So I want to do something else. So what I'm going to do is I'm going to define a few matrices. So I'm going to define a big, and by the way, this is actually also how you'll input things to libraries like scikit-learn. So this is not just mathematical. This is also actually when you form these things, you'll often form them in this way. So I'm going to define a matrix X, and sorry that I'm losing a little bit there. Hopefully, remember this equation. This is really important. But we have the least squares version there, so it's sort of okay. I'm going to first define a matrix X, which is going to be a matrix that has each individual example in our whole training set as a row in that matrix. So I have X1, and remember, we think of vectors as being column vectors. So to find a row vector, I'm going to transpose it. So I'm going to have X1 transpose as the first row here, then X2 transpose as the next row, etc., all the way down to XM transpose. So this is a M by N matrix, right? Because we have M different examples has M rows, and N, each input vector has N entries, so there are N columns in this matrix. We're also going to define a vector Y, which is the same thing just for the Y's. And here we don't need to be the Y's are just scalars themselves, right? So we don't need a whole row. Here we just have entries. So Y1, Y2, Ym. So when I write Y without a superscript, I actually mean a vector, not a single scalar. All right. So now sort of the key part is that I'm going to claim I can write this thing as this. Still the same, minimize over theta. But instead of that thing, oh, I forgot a 1/2 there. 1/2 x theta minus y, 2 norm, the Euclidean norm squared. Remember, the Euclidean norm of a vector is just defined for any vector z. It's just defined as z transpose z, which is just also equal, by the way, to the sum from all I equals 1 to n, if z is n-dimensional, of zi squared. Okay. So I'm claiming those two things are identical. And hopefully, actually, you can kind of start to see why they're identical here. If I look at this quantity in the middle here, this quantity is itself a vector that is m-dimensional. Oh, y here is also m-dimensional, I should add. This quantity in the middle of this norm here is a vector, which is m-dimensional, because if I take theta and I multiply it by x, the matrix x, then the ith element of that, so first of all, actually, let's just talk about the size here. So first of all, x here is m by n, right? Theta here is n-dimensional, and really as a vector, that really means n by 1. So the result is going to be a vector that is m by 1. So this whole thing is a vector that is m by 1. This is also a vector that's m by 1. And so the subtraction there is still a vector that's m-dimensional. Now, the entries in this thing, so the ith element here, x theta I, right? That is equal to the inner product of the ith row of x times theta. In other words, this is equal to xi transpose times theta, which is also just equal to, I could just flip the order, theta transpose xi, which is equal to our hypothesis function. Right. I hate this when you can't slide out this board here. It's getting harder and harder to write. So this term minus this term is just equal to the vector of all our errors between our hypothesis, well, not the errors, the vector between the difference between our hypothesis function and the corresponding y. Right? Take all those things and square them. So in other words, it's exactly this term here, is the ith entry of that matrix, of the vector. And then the 2 norm squared is just the sum of the squares of all the components there, which is just equal to exactly our objective over there. Yeah?
Remind me of the two subscripts.
Sure. So the two subject just means that it is a two norm. I'm not going to go into, it's just, there are other norms too. The one norm, for example, is a sum of absolute values. The infinity norm is the sum as the max of all the entries. We're not going to worry about, I mean, you can define arbitrary p norms actually in a way that generalizes all of these things, but the two norm is just the Euclidean norm, which is just this term. I mean, the norm without the square there is actually the square root of that, but the two norm squared is just that term. That's just the notation for it. Yeah. So why did I added the 1/2 just because if you remember when I first did the math before, I had all these annoying 2 terms that canceled out in the end. I just don't want to do that, and so I'm just going to scale it by 1/2. Doesn't change the answer, of course, right? Because everything is the same. So you'll see that a lot, though. A lot of quadratic forms, often they put the 1/2 in front of it for that exact reason. So you can ignore these annoying 2s. Okay, so I'm unfortunately going to have to. Yes, I didn't think this through because now I have to cover that up to write. All right, we'll do our best here. Okay, here's what I'm going to do. I'm going to write here the problem we're trying to solve. I should probably get used to using that board because it's much bigger, but I don't know why. Somehow writing this way is more, I'm closer to the slides this way when you're right-handed, I guess. All right, so the problem we're trying to solve is the following. We want to minimize over theta 1/2 of the 2 norm, it's not a, of x theta minus y squared. And we're going to do this exactly by taking derivative and setting them equal as 0. But it turns out that actually sort of doing that term by term gets very cumbersome. And there's very nice notation for doing this directly as a matrix expression. And so that's what we're going to do here. And this leads us to something called the gradient. So the gradient of a function is the simple generalization of a derivative to multivariate functions. So if we have some function f, which is a function from Rn to R, then the gradient, which I'm going to write like this. I'm going to write this as gradient upside down triangle. Sorry. Gradient of theta. I'll use theta rather than x here. It would just be confusing otherwise. Gradient of the theta of this function f. And I'm just using f here as sort of a placeholder for any function. It can be any function of theta. This is a vector of all partial derivatives. Right? So it's going to have the first partial derivative of f with respect to theta 1. The second one, theta 2, partial f, partial. And so, because it has n of these things, remember f itself is scalar valued. It has a single number that is outputting, but it takes as input a vector in Rn. And so I'm defining a vector of all possible derivatives, which is going to be a quantity, which is also therefore a vector in Rn. And the goal, or rather, just like for scalar valued functions, we had the condition that a 0 gradient meant we were minimizing, meant we were at an optimum of the function. If the function has if it has minima instead of maxima, doesn't have flat points, stuff like that. Just like that is the condition for a scalar valued function. The condition for us to be at a minimum or an optimum of a vector valued function would just be that the entire gradient is equal to 0. And in fact, we actually used this already. Because when I derived the equations, the derivatives with respect to theta 1 and theta 2 for our least squares problem, actually that was exactly a function with n equals 2 here, right? And I derived the two derivatives, and set them both equal to 0. And in fact, this is just a kind of a nice bookkeeping way of writing that with a single symbol instead of with lots of symbols. So the condition for minimizing a function, and again, a function of certain types, is that the gradient has to be 0. Okay. We'll get to that in a second. Let's talk about it being 0 first. So I'm only caring now about the fact that at the optimum, at a sort of a flat point, I mean, a minimum has to be a flat point, right? So a minimum has to be a point where the gradient is 0 for functions that have derivatives. How much time do I have? 4 minutes. Okay. I think I can finish least squares in that time. All right, I'm going to use two rules also, which I can use without proof. And you'll have to just sort of take my word for this. They're very easy to show, actually. You can show them out just term by term, the same just by going back to scalar calculus. But I'm going to use the following thing. I have some function, x times theta is equal to x transpose. Oops, there's no bar there. That was just a x transpose times the gradient with respect to x theta. In other words, whatever the argument of the function is of f x theta. And this is just an analog of the chain rule for single variate calculus, right? Where you have something like the f prime of ax, rather, I'll write it like this. The derivative of respect to x of f of a x, right, is equal to a times the derivative with respect to x of f of x, something like that, right? So you can just do the same thing here. Okay, that's the first rule I'm going to use. The next one I'm going to use is the gradient of the 2 norm squared. It's just equal to, in fact, 1/2 2 norm squared is just equal to theta. And this should be familiar to you because the derivative of x squared is equal to 2x. That's just the analog for the matrix for the vector term. And in fact, it follows exactly from the same reason. I added a little bit of extra thing there because it doesn't matter if there's another term here. So if we have x minus z squared, that's just 2x minus z. Okay, so now we have everything we need to solve these squares. So I'm trying to solve that problem up there. So I'm going to take the gradient of that function way up at the top. Everyone see that one still? It's just our 2 norm term. So the gradient, so we want to find the gradient to theta, x theta minus y, 1/2. Which by these rules, and I've sort of handed wavy here because I'm just going to apply them and not worry about deriving them. Again, if you want to derive them, you just derive them term by term and show that it's true for every term in the gradient, and then therefore it's true for the whole gradient. This is going to be equal to x transpose times the gradient of this guy, which is just the second rule, x theta minus y. That's our gradient. We then set this equal to 0. And then we'll just sort of move terms around. That will imply that x transpose x, theta, equals x transpose y, or in other words, theta equals x transpose y, or sorry, x transpose x inverse x transpose y. This equation is so famous it has its own name. It's called the normal equations. It is a matrix form of exactly the set of equations we derived sort of term by term in the first example here. The nice thing here is it does not matter how big x is. It can have, 20 features, 30 features, a million features. It still holds here that this is the case. With a million features, you have to be a little careful because this thing has to be invertible, which I won't talk about right now. But as long as it is invertible, which we'll actually mention in a second, or later, very shortly in the class, this equation gives you the solution. And as a quick sort of example here, I can actually use it in the same data here to construct this feature vector where we have the high temperature, the weekday, a constant term. You solve just this equation like this. You get coefficients for each of these three terms. So theta is now a vector in R3 because there are 3 features. And this actually gives you the coefficients you need to determine what the consumption will be, looking at the temperature and whether or not it's a weekday or a weekend. So, and you can, of course, include more and more. It's harder to plot at that level, but here I'm showing the 2 plots now, both for the of this function now for the is weekday case and the is not weekday case, is weekend case, and so it actually does the weekends. The consumption on the weekend is substantially lower than during the weekdays. Okay, so that's actually farther than I intended to get today, so that's great. We'll pick up next time, finishing up linear regression, talking about other methods for optimizing these things, and then also talking about classification. Oh, the tutorial. I think I mentioned this, but I'll actually post some Piazza right now. If people want to come to office hours, I'm holding office hours in gates 8102 at 2:30. So after the lunch, there's going to be office hours. I'll see everyone. We'll see some people there if they want to come.